This is Chapter 4, Part 2, Basic Logic Gates. In this video, we're going to learn about basic logic gate alternative representations and how they're used to implement and understand the logic flow of Boolean expressions. Let's do it. For each logic gate, there's an alternative logic representation which completes the logic description of that gate. The alternative representation of a gate does not change its electrical or logical function. It describes how the gate logically operates for all combinations of inputs. So what do we mean? Well, first of all, when we look at a logic circuit, we want to be able to understand the logic flow within that circuit. So, in order to understand it better, instead of naming or saying this is an AND gate right here, we'll call it an OR gate. So this symbol, which is an AND symbol, we'll call it an OR gate. And this symbol, which is an OR gate, we'll call it an ANY gate. This designation of all and any helps us describe the logic flow. The NAND gate symbols would be organized as such, NAND and NOR symbols. The NAND gate would be, since it's an AND with a NOT on the output, it'd be called an ALL. And the OR gate with a inverter on the output, inverter bubble on the output, would be called an ANY gate. So how do we read this? Well, the way we read it is, first of all, we say the name of the gate, which is ALL, and then we look at the inputs. If there's no zeros on the inputs or no bubbles on the inputs, we say high. And then we say it gives a, and then we look at the output, and if there's a bubble, we say low. If there's no bubble, we say high. So for instance, for this ALL gate, we say all inputs high, because there's no bubbles, all inputs high, give a low, because there's an output bubble. And then for the NOR gate, we say any input high gives an output low. Again, any input high gives an output low. This just gives us an easier way to describe logically, when we're looking at a complex circuit, exactly what's going on. This allows us to logically understand a little better when we're trying to understand how circuits work, the implemented circuits work. Okay, so let's look at the AND gate and the OR gate. First, the AND gate. The AND gate says all inputs high, these are high because there's no bubble, gives you a high, output is a high. The OR gate says any, you say the word any, input high, because there's no bubbles, any input high gives an output of high. So any input high gives an output high. Okay? High, high, high. Okay. For the NAND gate, we would say all inputs high give an output of low. So all inputs high would give an output of a low. For the NOR gate, we would say any input high gives an output of low. Okay, how do we convert between gate representations? In other words, how can we go from an all to an any or an any to an all? Well, this is the way we do it. We say that you can start with an all gate, which is an AND gate. We'll say you start with an all gate and you convert it to an any gate by changing the all to an any and inverting the inputs and inverting the output. Again, you start with whatever you're starting with. In this case, it's an AND gate. We change the all to an any, and then we invert the inputs and invert the outputs. So this gate on the bottom says that any input low, because there's a bubble, any input low gives you a low on the output. Any input low gives you a low on the output. Let's go the other direction. Let's start with a OR gate or any gate and convert to an all gate. So the first thing we do is we change the any to an all, and we invert the inputs and output. So this is what we get when we do that. The OR gate goes to an all gate, and the all gate says that all inputs low give an output of low. All inputs low give an output of low. Okay? So now let's look at a 2-input NAND gate and its normal designation, which is the NAND symbol right here, and then the alternate symbol representation, which is an any with the inputs inverted. So if we look at a truth table for this particular NAND gate, we see that when both A and B, when we have two ones, when A and B are 1, all inputs are 1 or high, the output is going to be a 0. And that's what we have, right, because we have a bubble on the outside. So all inputs high force the output to a 0. Okay? Well, this same gate, which is this one right here, because if we do a conversion from all to any, for this NAND gate, let's convert it. It's going to go to the any symbol, and we invert the inputs. Okay, we invert the two inputs, and we invert the output. Well, it's already got a bubble on it, so we put another bubble, add another bubble, which just makes it not inverted. So that's this alternate representation. So in a truth table, there's one symbol that represents the logic flow for one particular case in the truth table. In this case, it's the NAND gate. It says that all inputs high give you a low. And then for the other three cases in this truth table, A, B, 0, 0, 0, 1, 1, 0, this any symbol says that any low, okay, any low, well, there A is a low there. Any low gives a high. Well, we got a high. A is a low, C is a high. The same with B is a low, either A or B, either is low, the output's high. Okay, let's look at the second case. Any low gives a high. A is low, B is a 1. Well, any low on the input gives you a high. That's what this one is. Okay, let's go to the third and final. This says A is a 1, B is a 0. A is a 1, B is a 0. That says any low gives a high. So this particular logical representation is the alternate representation of the NAND gate. So this is still a NAND gate, but it is an alternate logical representation that helps us understand exactly what's going on for these three cases, because we can look at this gate, this alternate representation, and we can see that when any one of these are low, because it's an any gate, the output's going to be high, and that's in these three cases. And alternatively, for the NAND gate, the other NAND gate representation, it says that all inputs are high. When all inputs are high, the output's going to be low. Same with a 3-input NAND gate alternate representation. Again, there's only one case when this logical symbol right here is true, and that's when A, B, and C are all 1. So we've got to have 1, 1, 1, and then we'll get a 0. Okay, for all the other cases, we use the alternate representation. This right here is also a 3-input NAND gate, but this is the alternate representation, which is logically describing exactly what's happening in the truth table. Just like the previous 2-input NAND gate, any of these inputs low, and then you don't care what these two are, the output's going to be high. So for all these cases, there's a low in there, there's a 0, so the output's going to be high. So it describes all these cases right here. So you have two logical representations which define the complete truth table. Let's look at a 2-input NOR gate. 2-input NOR gate, for the NOR function down here, it's an any gate, and the any gate says that any input high, either A or B, the output's going to be low. So let's look at the first case here. We have 0, 1. So any high gives a low, so it's going to be 0. Okay. The second case we have is 1, 0. Well, any high gives a low. Okay, so that's taken care of. And then the final case we have 1, 1. It says any high, well, they're both high. Well, it says any one of them high is going to cause the output to go low. So that's this case right here. Well, for the final case, logically, what is the alternate representation is going to define what this case is right here. This says that when A and B are both at 0, this says all lows, A and B are both 0, all lows give a high. And so that's what this is right here. Okay, so this is the NOR gate alternate representation, which is representing this one case, and then the other 3 cases are represented by the standard NOR symbol. But logically, they're both NOR gates. This is the 3-input NOR alternate representation. So if we look at the 3-input NOR gate standard symbol down here, it defines these 7 combinations from 1 to 7. Okay, and what it says is any one of these are high. We don't care what the other 2 are. The output's going to be low. Okay, any input high. Well, there's a high, there's a high, there's a high, there's a high. So we've got 1s all the way down. The output's going to be 0. So these 7 locations describe exactly what's going on with this standard NOR gate. The one and final one that is the alternate representation for the NOR gate describes what happens when all inputs are low. So 0, 0, 0. This says all inputs low because there's a bubble there, gives you a 1. And that's what this one is right here. And finally, for the alternate representation for an inverter, it just says that when A is low, B is high. So this is a 0, this is a 1. Or alternately, when A is a 1, B is a 0. So you can put the bubble on either side of the inverter and it doesn't make any difference functionally, electrically and functionally. Okay, let's look at a 4-input NAND gate, alternate representation. The alternate representation of a 4-input NAND gate is you look at to create the alternate representation. You change this all to an any. So the all says when we have all 4 1s, the highest value, 1, 1, 1, 1, the output's going to be 0. So when you have 1, 1, 1, 1, the output's going to be 0. For all the rest of the cases, there are 16 cases here. So the rest of the 15 cases, it says that any low, any 0 on any of the inputs, so you can have 0, X, 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 or any 0 anywhere in this combination of inputs, the output's going to be a 1. So this describes the case where they're all 1s. When you have A, B, C, D, all 1, that's 15. And the other 15 combinations from 0 to 14, this logical symbol describes the functional operation of the circuit. Okay? And I drew the Boolean expression for the 4-input NAND gate and the 4-input, this particular function here, any gate. As you can see, this is the De Morgan of this. It's equal to A bar plus B bar plus C bar plus D bar. Okay, so they're logically equivalent. Let's do an 8-input NOR alternate representation. This is an 8-input NOR, and we'll call that an any, like we designated before. And then we want to convert the alternate representation of this 8-input NOR. And we change the any to all. And this describes the one number where the output is going to be a 1. Well, what is that? That says when all inputs are low, the output's going to be a 1. So 0, 0, 0, 0, 0, 0, 0, 0. Okay, so how many input combinations are there? Well, there's 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's 2 to the 8th combinations. That equals 256 different combinations. It goes from 0 to 255. So 0 is this case down here. And then the other from 1 to 256. I'm sorry, 1 to 255. Will be for all the other combinations. This will logically describe from 1 to 255, the operation that says any high gives a low. Let's look at some more examples of alternate representations, and we're going to look at an AND and an OR gate. And again, we know this is a ALL, and this is an any. So what this says is all highs give a high, and that's this classical AND gate. The alternate representation says any low gives a low. Okay? And if we look at an AND gate truth table for 2 inputs, okay, it says all highs give a high. So that's this one right here. So this case covers that one. And then the other case says any low, well, there's a low, gives a low. Okay. Any low gives a low. There's a low. We get a low. Any low gives a low. We get a low. Okay. So this is the alternate representation of an AND gate that logically describes the other 3 cases, the other, I like to call them any cases. Let's look at a 2-input OR gate. So this is an any, and this is an all. Let's draw that truth table again. Whoops, I thought it was a Cardinal map for a second there, which it's not. Okay, let's look at the top function here, this OR gate, which is an any. This says any high gives a high. So any high gives a high. Well, there's no highs there, so any high, there's a 1, we'll get a high. Any high gives a high, we get a high. There's 2 1s there, so we get a high. What's the alternate representation say? We converted it by inverting the symbol and inverting the inputs and outputs. So this says all low gives a low. So all lows give a low. So this one right here describes these 3 cases, and this one right here describes this case. Okay, in summary, we learned what basic logic gates are and how they function. We introduced the concept of any and all gate descriptions to help us understand the logic flow of the circuit implementations. And we're going to do some more examples of that and show how it's easy to understand, look at a circuit implementation and understand the logic flow. And it's good for when you have a problem going in and debugging the problem, figuring out, gee, is this logic design wrong, or is it wired wrong, or whatever. It helps you analyze the circuit functionally to make sure it's operating correctly. And also the importance of alternate representation of logic was discussed with the goal of helping to understand logic flow, which is what we just talked about. Thanks for watching.